Now students, the next type of atomic radius is the van der Waals radius. Now what is a van der Waals radius? It is, we can say, it is a half of the internuclear distance between the two adjacent atoms of the two different molecules, or we can say of the two adjacent molecules in the nearby, right, of the same substance in the solid state. Now you can have the view on the definition here. What is the van der Waals radius? It is the half of the internuclear distance between the two adjacent atoms of same element belonging to two nearest neighboring molecules of the same substance in the solid state. Right, students? So here we will just first see that the two adjacent atoms of the element belonging to same nearest neighboring molecules. Now let us consider here that this is one molecule atom. This is the another atom covalently bonded. Right. Now the neighboring molecule. This is the neighboring molecule of the same substance, and here too the two atoms, they are covalently bonded. I think this is clear of the line that the two nearest neighboring molecules of the same substance in the solid state. Why the solid state? So that the molecules can come closer to a maximum, closer they can approach one another, right? So here we are going to find out the half. This is clear, this last line. Now the two adjacent atoms, this and this atom are not adjacent, this and this are adjacent, so we will take this one atom and this atom, right? And we have to take the half of the internuclear distance of it. This is the internuclear distance and this is just the half of it. Right, students? So half of the internuclear distance between the two adjacent atoms of same element. Now this element should be same. If it is A, this should be also A. This can be either same or different, right? Can be B or B, right? Or A again. Let it be in this way, right? In that case, this is the half of the internuclear distance, right, between the two adjacent atoms of the neighboring molecule. Now these neighboring molecule will be of same substance in the solid state. So student, this distance will be known as, that is from this one, will be known as the van der Waals radius. It is expressed in, written in this way, r van der Waals radius. Right, now the van der Waals radius, right, it is have the larger distance, then it is greater than the covalent radius. So we can say that covalent radius is shorter than the van der Waals radius, because in the covalent radius we have got overlapping of the atomic orbitals, which brings the two atoms closer, right? Whereas in the van der Waals radii, the two atoms are away from, two atoms between the two adjacent molecules of same substance, they are not close enough, right? They are not fused with one another, they are just away from one another. So that's why the covalent radii is shorter than the van der Waals radius. So just get it noted down. Now students, the next type of radius is the metallic radius. Now this is observed in the metals. In the metals, the atoms are arranged in a definite order in a crystal lattice. Now what is a crystal lattice? A three-dimensional arrangement of the metal atoms, right? Having a definite pattern. So the distance between the two closest metal atoms will be considered here. So in the metallic radius, we take the half of the internuclear distance between the metal atoms, or two metal atoms in the crystal lattice. So what is the metallic radius? It is the half of internuclear distance between the two nearest metal atoms in crystal lattice, right? So there will be an array of metal atoms like it is in this way, right? So I'm just showing it a pictorial representation where I am on the board expressing the two-dimensional representation of the crystal lattice, but actually it's a three-dimensional arrangement, right? So but on board it is possible to draw the here at this moment to draw the two-dimensional one. So here the two closest neighbor are these two, either this two or this two or this two, any of the two closest metal atoms. So we will take the internuclear distance, get it half, we will get the metallic radius. Now the metallic radius, or simple you can write down our metal, the metallic radius, right? It will be greater than the covalent radius, right? So just a simple question to you all, that if you just compare the metallic radius, covalent radius and the van der Waals radius, which one is going to be of shorter distance, right? So metallic radius, covalent radius and the van der Waals radius, which one will be of greater magnitude? So here the covalent radius, hope so you are able to just arrange the series. So covalent radius will be shorter or shortest, then comes the metallic radius, right? And at last we have the van der Waals radius, so you can simply write down van der Waals, VAN, right? So these three mainly comprises the atomic radius, and we have one more expression of the atomic size, that is the Ionic radii, but that we will discuss later. First we will discuss the variation of the atomic radius across the period and down the group, right? So far as atomic radius is concerned, we deal with only metallic covalent radius, metallic radius and the van der Waals radius. So we will discuss now the variation of the atomic radii across the period and down the group. So next we are continuing here, variation of atomic size or radius, right? So this we will first have the across the period. Now students, generally the atomic size on moving across the period from, we can say, group 1 to group 17, will not include group 18 here. Now from group 1 to group 17, when we move across the period, in a period, the atomic size decreases, right? So on moving across the period, atomic size decreases from group 1 to group 17, right? So can you tell why? Because here there is the increase with every increase in the atomic number, there is increase in the we can say increase in the nuclear charge. The one electron will be added. With increase in the atomic number, there will be increase in the number of electrons, right? in the shells also, right, in the same shell, and the simultaneously the number of proton in the nucleus is also going to increase, right? Therefore, the effective or nuclear charge increases and the shells are being pulled in. Right, student? So, on moving across the period, there is decrease in the atomic size because due to increase in the nuclear charge, definitely there is increase in the number of the electrons also by 1 unit, right? But the magnitude of the nuclear charge which has been increased in the nucleus, right? It dominates, and the electrons on the outermost shell, they are pulled in. So as a result, the size decreases, right? But in case of group 18, because group 18 also belong into the same period, but in case of group 18, we will not consider the covalent radius. Here we are going to consider the van der Waals radius, right? So that's why there is an increase in the size of the group 18, right, with respect to that of the group 17. So from group 1 to group 17, we are considering here the covalent radius, and for group 18 we don't have a covalent radius. We consider there the van der Waals radius, which is larger in magnitude than that of the covalent radii. Now next is the down the group. When we move down the group, so what happens? There is increase in atomic size or radius on moving down the group. So students, here what happens that with the increase in when we jump from one period to the another period, right? That means when you're jumping down the group, then there is increase in the atomic number, right? And the new electron or the incoming electron is added in the new shell, right? Definitely the proton is also increasing, but the increase in the shell predominates here the nuclear charge attraction. As a result, what happens, there is an increase in the atomic size of that element, right? So we have discussed here the variation of atomic radius on moving across the period and on moving down the group. Students, you will just get it noted down in your notebook where you are discussing the atomic size, their types, right? How many types, what first will be the how you're going to define an atomic size, right? And why can't we just get the radius of an atom, right, simply, and we can just write that the atomic size can be expressed in term of atomic radius, or it is the distance or radius of an atom is called as atomic size, right? Why we can't say so? So we have discussed it that since the atom cannot be isolated, it's too small to get it measured down, then the probability distribution curve tell us that there is no well defined probability boundary diagram doesn't tell us about, there's no well defined boundary of an atom, and the atom is not always surrounded in this with the same environment. There is always a change in its environment, and the bonded state is also going to change, right? Students, you will mention there is all state and then you will express it, that hence that's why we are having the atomic radius expressed in term of at covalent radius. Then we have got the van der Waals radius and the metallic radius, right students? So that this thing you will get it noted down in your notebook. Okay, good morning students. Today we are just continuing the unit 3, and our topic was atomic radius, and we have discussed the types of atomic radii. First was the covalent radius, second was the van der Waals radius, and third was the metallic radius. Now students, these radius, when they are just studied about their variation across the period and down the group, we found that when moving across the period, the atomic radii or the atomic size is going to decrease from group 1 to group 17, and moving down the group, the atomic radius increases. Now students, today we are going to discuss about the ionic radius. Now, what is an ionic radius? Before that, we have to go through it, how the ions are being formed. Now, in a neutral atom, by losing or gaining an electron, an ion is formed. If a neutral atom loses an electron, it will form a cation. And if it will accept an electron, it will form an anion. Now students, with the two oppositely charged ions, that is the cation and the anion, they will come closer. A bond is formed which is known as the ionic bond. So here the ionic bond is formed by the lose or gain of the electrons. Now students, the ionic radius, it is actually, we can say, the internuclear distance between the two ions, right? We have to first find out the internuclear distance between the two ions, and then we are going to just sum up that to be radii of cation plus radii of anion. Now when we are going to define it, we will define it as the, we can say the distance or the effective distance till where the nuclear charge influence of an ion is going to execute in a ionic bond. So students, I have written a definition on the board. You can have a just view on it. So ionic radius, it is the effective distance from the nucleus of the ion to the point up to which it has an influence in an ionic bond. Now when we say it has an influence, it means that if it is a positive charge or a cation, it will have its attraction, right, for the negatively charged ion. Similarly, a negative charge ion will have the attraction for the positive charge ion. So their effect, okay, for how long their effect is going to execute or is going to work, right, from the nucleus of it, right, will be known as the ionic radius. Now, if we consider this as a cation, right, students? So here let it be A plus. This is a cation, and this is an anion, right? Now, this is the nucleus of their, we can say, the atom, or now they are the ions, right? Now, the influence of it. So, this part will be known as cationic radius. And similarly, this part, we can say this one will be known as the anionic radius, right student? And the sum of these two, R plus and R negative, is known as the interionic distance. So interionic distance between these cation and anion is R plus R negative, right student? So the ionic radius, it is the, we can say, the distance from the nucleus of the ion to the point up to which it has an influence in an ionic bond, right students? So hope so it is clear to you. So what will be the cationic radius? The cation, that is the ionic radius of an cation, is known as cationic radius, and the ionic radius of an anion will be known as the anionic radius. And the interionic distance between the two ions is uh, calculated, or is we can say observed through the X-ray diffraction studies. Now students, we are going to compare the size of the cation and with its parent atom, and the size of the anion with its parent atom, right students? So we will do it first. We will just check that the size of the cation and the size of the parent atom. Now, for that, let us take an example of sodium. So sodium, right? So what is the configuration of it? It is 11 atomic number. So we will have it 1s2, 2s2, 2p6, 3s1, or we can simply write it as a 281 configuration, right? So it has got a configuration of 281. Now, when it loses an electron, now here student, Na is losing an electron and it is forming Na plus. Now, the electronic configuration changes from 281 to 28. That means the electronic configuration, we are talking about electronic configuration here. The species will remain the sodium only, the sodium ion, right? So here the sodium is the parent atom and this is the cation which has been formed. Now students, we are discussing here or we are going to compare the size of the cation to that of the parent atom. Now, it has been found that the size of cation is smaller than parent atom. So, size of cation is smaller than the parent atom. Now students, if you see here that what's the difference here? The number of the protons in sodium is 11 and that of the proton in the sodium ion will be also 11 only, right? Only difference is that here the number of electrons in sodium is parent atom, it is 11 and here it is 10. So we can say that here the in sodium in the parent atom 11 protons are pulling the 11 electrons to it, right? Whereas in sodium ion, the 11 protons are pulling the 10 electrons. So here students, 11 protons are pulling the 10 electrons and here students it is 11 protons pulling the 11 electrons. So tell me where is the magnitude of nuclear charge will be more. Or we can say the effective nuclear charge which will be getting applied on the electrons, right, will be more in sodium ion. So we can say that if the nuclear charge, effective nuclear charge is more, then the size is going to shrink and hence the size of the cation is smaller than that of the parent atom. So students, the size of cation is smaller than parent atom. Why? Because the effective nuclear charge on the cation is greater than the parent atom. Therefore, the outermost electrons are pulled more inside in cation. Hence, the size of cation is smaller than the parent atom. Right? Now, we will just go through the second part of it, that is the size of the anion is bigger than that of the parent atom. So students, let us take an example first. Let it be chlorine atom, it's a neutral atom and you know its configuration is 287. You can write down the configuration in the term of shells and subshells also. right? And the orbitals. So chlorine accepting one electron and it is changing into chloride ion. Now when it does so, here the configuration of electron is now 288. Now students, here you will see that 17 protons are pulling 17 electrons. But in this case, here the 17 protons are pulling how many electrons, students? 18 electrons. Now, where do you think the magnitude of the nuclear charge? Right, we can say that the effective nuclear charge, where it will be more? It will be more here. Here it is going to be less because 17 protons are pulling 18 electrons. So definitely magnitude of the effective nuclear charge will be less here, right? And here it is going to be more. So that's why the size of the parent atom, this is the parent atom and this is the anion which is formed, right? So if we just compare the size, so size of parent atom will be smaller than the size of anion. So we can just write here now that the size of anion is larger than parent atom. Now here it is why? Because the effective nuclear charge on the anion, so because the effective nuclear charge on the anion is less or lesser than parent atom, therefore the outermost electrons are less effectively pulled inside, hence size of parent atom is smaller. Right, students? So size of anion is larger than the parent atom. Why is it so? Because the effective nuclear charge in the anion is lesser than the parent atom. Right, the effective nuclear charge. So here you can see that so 18 electrons have been pulled by the 17 protons. So here the nuclear charge which is operating on the 18 electron will be lesser in comparison to that of the parent atom. So the parent atom, in parent atom the outermost electrons will be pulled inside more strongly, right, and hence they are going to be smaller, whereas in case of anion the size is going to be more.